Hi there and welcome along to another video. How are we doing? So we're going to look at the Young slit equation. I'm not going to look at the derivation, we're just going to keep it simple today. But we're also going to look at the patterns that are formed when light passes through a double slit and a single slit, in terms of the not just the patterns but the graphs of the patterns as well. So we'll start off by imagining a really thin single slit. We have some nice coherent light from a laser incident on our single slit, and as you know, the light will now spread out by diffraction as it passes through the slit, and we'll see a pattern on the screen. So what we'll see on the screen in the case of a single slit, and I will try and get a photo of this actually in action at some point, is a very large central bright spot and smaller bright spots on either side. And let's be absolutely clear, the exam board are absolutely certain that you need to know that, and we're going to use it quite a lot. This central maxima is exactly twice the width of the side maxima. Another way that we can very usefully represent this pattern is via a graph of intensity going in this direction versus angle. So that's the angle measured like that. We're going to be making a lot of use of that angle. And the graph that we would see, well, we can sort of line it up, can't we? We can see in the centre we've got very bright light. It then falls rapidly either side here and here to be dark. So there's our central maxima, and then on either side, each one of those little side fringes is a little hump like that. And you might be asking, well, how does that happen, John? And it's quite hard to explain, and I'm just going to kind of give you a hint. If we can imagine some waves setting off from that side of the slit and some waves setting off from that side of the slit, at a dark point like this, where we have destructive interference, the path difference between this edge and the centre is half a wavelength, so they're out of phase, so we get destructive interference, and we get a dark spot on the screen. If that light from here cancels the light from here, the light from here cancels the light from here, the light from here cancels the light from here, and we get a dark spot. But moving on, now we're going to imagine our coherent light arriving from the laser at a double slit. So you know what the pattern will look like, and you know why it forms. Let's just make sure, remember these are fringes. We know why, sorry, not why, we know how to draw this graph. Okay, so each one of these peaks is now going to be, the graph goes up. If you're a mathematical person, what I'm trying to draw here is a sine squared graph. Now, in the idealized perfect case, that's what the graph would look like, and that's where each slit is kind of very, very thin, and we get a huge amount of diffraction and spreading out. In reality, actually what we get is somewhere between the two patterns, and you could see that in the photos I took last time, because of the way the light spreads out from the individual slits. We kind of get that pattern shoved inside that pattern. But these will do for the exam board, and I think for the moment we're just kind of trying to get through on what we need to know. Nice equation linking all this up, really, really straightforward. Capital D is the distance from the slit to the screen. The distance, and this is always measured between the centre of the slits is S. The distance between the bright fringes, which is the same as the distance between the dark spots, is W. And that just leaves us lambda, the wavelength. All have to be measured in the same units, and that would normally be meters. And we simply get lambda equals WS over D. So we can use that equation in a very straightforward way. We just have to know 3 of the variables and we can calculate the other one. So for example, if I got a double slit, we knew that distance. We measured with a ruler the distance between the bright spots, measured the slit to screen distance, we could calculate the wavelength of the laser. Okay, thank you very much.